Hey everyone. Okay, so we're going to go ahead and review just really quickly what it is that you did already in section one, in part one, and then I'm going to kind of go on into part two here. Uh, but for this whole exercise, for module five here, what we're talking about is we are talking about watersheds here. And I know maybe some aren't entirely familiar with what a watershed is. So what a watershed is it is the area that contributes overland flow to some designated output point. Whatever it is, if we want to go ahead and designate our output point as the mouth of the Mississippi River, then every point of the continent that contributes any flow into the Mississippi River that then goes ahead and flows down the Ohio, the Missouri, or the Mississippi, whichever tributary it may flow down until eventually comes on out by New Orleans at the Gulf of Mexico. So the watershed of a stream is going to be the total area which contributes overland flow into the output point that we designate. Um, based on flow of the land. So that's what I mean by overland flow. In this case, what we're talking about is the West Fork of the Gallatin River. This is up in the Big Sky area, and let's go ahead and take a quick look here at our model. So we started with our digital elevation model, and then we went ahead and we ran the watershed. So I'm going to go ahead and search for watershed here, and here under the grass model, we can see our watershed model here. Here we go. So we're going to go ahead and we're going to run watershed. Hopefully this ran relatively quickly for you. And so we're going to go ahead and make sure our West Fork DEM is the model. And we were setting our minimum size of exterior watershed basin to 5,000 cells. Now, again, this is in cell count, not in any metric value or anything. Everything else here, and I'm going to go ahead and simplify this quite a bit more than what we were doing. I'm going to go ahead and say, yeah, we don't care about the flow. Well, we'll go ahead and draw the flow accumulation. I'm going to go ahead and get rid of those half basins. I'm not going to need those right. Well, let's go ahead and run it. It doesn't take much more time. Okay, so I've gotten rid of all the ones that I had you get rid of here. I'm going to go ahead and run that. It should only take a couple of moments to run this. And you can see that came out quite nicely. The order in which it draws these is always regrettable. So it, for some reason, likes to put the stream segment. Oh, the stream segments are on top. Oh, that's right. But can't see them because they are colored the same as the basins that numbered them. So if I go ahead and do this now, we can see our colored numbered stream segments here. The difference that you may see if we run this model again, and so here I'm going to go ahead and let me get to where you can see what I'm doing with the mouse here. If we take a look at our history, and I'm going to go ahead and I'm going to bring up watershed again, except that this time I'm going to go ahead, I'm going to change this. Let's cut this in half down to 2,500 and run the model again. This might take just another moment to run here because it's a little bit more dense. So I'm going to go ahead and pause for a moment while that runs. And that ran. So it took a minute, and now you can see if we take a look here at our stream segment, when I took that down to 2,400, let's go ahead and turn off some of these other layers here. Oh, I didn't simplify anything, but you can see that there are more stream segments that are defined now than there were in the previous. So just collapse all of these. And so if I toggle between the two versions of the stream segments, you can see how many more how many more have been generated just by changing the parameter from 5,000 down to 2,500. So what that's doing is it's delineating with a stream segment by cells that have had, at least in the case of our original model, 5,000 cells have flown into a point before it becomes delineated as part of the stream. In this case, we cut that to 2,500, so it required less contributing area to flow into it, so the stream segments get quite a bit more extensive. So I'm going to go ahead and get rid of these because I like our 5,000. So go ahead and remove those layers. And what are you doing here? That took just a moment. So now you can see we've got our stream segments back. And so these stream segments are areas, which is why they are drawn as a raster. You may wonder, why is this model putting out streams as a raster rather than as vector? And of course, we dealt with that manually by running the vectorize tool. But the reason for this to be a raster in the first place is because the area that is being, or the cells that are being described as the stream channel are actually cells that have a flow accumulation value, and that is this number of cells that drain through each cell. If we go ahead and we identify on these cells, we can see that their value is going to be greater than the value over 5,000. So let's go on back to our stream segments here, and the next thing that we did was we ran the thin model. And I think it's a little hard to understand necessarily why this was even a necessary step. Why didn't we just go ahead and run our vectorize right on stream segments, because they certainly look linear to me. Well, let's go ahead and run that again. So I'm going to go ahead and I'm going to run thin on my stream segments. So I need to find stream segments here. Thin. And so our thin stream segment, close that, and we take a look. This is up here. The ordering isn't always great. If we toggle between, you see there's not a whole lot of difference, but I'm going to go ahead and turn my thin layer into a mask essentially here. And to do that, I'm just going to go ahead and I'm going to select all these values, and I'm going to change all the colors to black. So just go ahead and do that. And so if I change all the values in the thinned streams to black, you can see, and I did that just to turn them into a mask, and you can see if when I do that, there's still a little bit of color of those original stream segments coming through. And here you can see that there's places where the thin segment, or the unthin segment, can be a little chonky. There's a little bit of ambiguity here. Which way is the stream actually flowing? So once we thin it, then we make sure that at all points, the stream flow is actually restricted to a single cell. There's no ambiguities. There's no fat points like what we see here. So there's no reason for this to be so many points when it can really just be flowing through at an angle like this. So the thinned lines, so let me go ahead and let's turn those into a nice stream happy kind of color. Let's make it a nice blue like that. And so now we can see what our stream color looks like in the thinned version of it. So let me go back to there. Excellent. So okay, so we've thinned our raster version. Looks like I missed a few values in there, but I'm not going to beat myself up over that too much. And so the next thing we needed to do was we needed to vectorize that. So I'm going to go ahead and I'm going to clear that out, and I'm going to vectorize. Vectorize. There we go. Vectorize thing here. And I actually realized I am obscuring the view here, but yeah, actually I'm saying that wrong. It's not vectorize, it is artivect. So I'm going to go type in artivect, not vectorize, and here's our artivect. And so we're going to go ahead and we're going to raster to vectorize the thinned, turn it into a line. Everything else in there should be good, so I'm going to go ahead and run that. And there we go. And now we've got a very nice vector version of our thinned raster, line. So if we are going to go ahead and portray our streams as a vector line, so at this point we now have a good stream, but we're going to hang on to those vector or those raster versions of the stream because those are tied into the model in a way that we're going to use here. Let's go back to our model here, and what I wanted to show you now was our how to go ahead and create a watershed boundary. So again, keeping in mind that the watershed is the total area that is contributing to the flow of water over the surface of the land. I'm going to go on down here, and it's the area that flows towards an outlet. So I'm going to go ahead and I'm going to choose my input raster, and in this case, the input raster is the drainage direction. This is the this is the direction that water is flowing over the land. So you can think of it as the downhill 90-degree 90-degree coefficient of the slope or the aspect of the slope. Okay, so if you've got a slope, some hill slope that's pointing and has an aspect of some direction, the 90-degree down direction, essentially the aspect is the down is going to be kind of the same calendar direction, but it's going to have a direction to it. So this is what we're looking at here when we're looking at the drainage direction. So our drainage direction, this is also called flow direction. And if you're working in the ArcGIS world, the flow direction is the way we do it. And then to designate our outlet, we're going to go ahead and we're going to click on the map here. And in order to do that, I want to bring our stream segments back up. So let's go ahead and so we're talking about the West Fork of the Gallatin. So I'm going to go ahead and I'm going to zoom in here. And I'm going to get right up against the Gallatin. Well, let's do it. Let's get right up against the Gallatin here. And I'm going to click. And so it's going to go ahead and feed in those coordinates. And let's run it. You can see how nice, and this is a really computationally efficient watershed tool here. This is one thing that Q does really, really very well is these watershed tools. Well, running, of course, the grass analytical tools running within the Q environment. So here we see our basin. So this is the watershed basin for the West Fork of the Gallatin River here. Very nicely delineated, nice and well done. And that was run based off of the pour point here, the outlet, where I clicked onto the map right here is where it went ahead and created all the different cells. So every cell in here flows along some flow direction until it gets to the stream channel here, then flows down the stream channel until it gets to that outlet point. So hopefully the meaning of that is sensible, and where this can really come in handy. Let's go ahead and I'm going to go ahead and get rid of that one here. Here, I'm going to go ahead and just duplicate it instead of removing it. Sloppy clicking. Okay. Oh boy. I just got rid of the layer that I wanted to keep. Well, let's see on my thinned one, that'll be fine. So That's going to be just fine. I don't need to recalculate it. But let's take a look at, let me get rid of that base again here. And so let me go ahead and run this model one more time really fast. I'm going to go to my history, and I'm going to bring up my water outlet, but I'm going to go ahead and I'm going to redefine my pour point here. And let's say we're examining this channel, and we are a water quality expert who is studying this channel here. And so here is the contributing watershed for this channel. But somewhere along this channel here, we've noticed that we have a contaminant that's being introduced into the flow of the channel, and a water quality test up on this reach of the channel does not test positive for any of this contaminant, whereas a water quality test down at this end of the channel tests positive for that contaminant. So what we might want to do is I'm going to go ahead and I'm going to generate two different watersheds. And so let me go ahead and I'm going to run my model one more time here. And so I'm going to do this, and I'm going to go ahead and zoom on in. And let's say our clean water sample is coming from this point here. And it's given us, oh, it's rendered it in the same color, so I'm going to go ahead and change the color here to green, because that is the clean one. And now what we can see is we can see this area here is the contributing area of, we can see that this is the contributing area of the clean sample point. And this area here that is still visible in yellow, without the green, this is the contributing area of this lower sample point. But if we were to look at the difference here, and so the area that is visible in yellow but not part of the green, we know that the contamination that is being measured at this lower sample point down here is being introduced into the stream channel somewhere within this smaller basin. So this difference in the watershed basins can yield some really valuable analytical results. So this is the analysis that we're going to do here for this section. I want you guys to go ahead and participate and follow along, and I want you to generate a similar differencing. Now then, in GIS, we tend to have these processes that we run a lot, that we tend to have to go ahead and do the same analyses over and over again. And as you can imagine, it gets to be kind of a pain to go ahead and hunt for our watershed outlet and everything every time, especially if this is a multi-step process and we need to do it over and over again. There's really no need for us to have to go through every one of these steps, when actually what we can do is we can automate the process. Okay, so the way that we can automate this process is we're going to go ahead and we're going to build a model to do this. Now, you'll notice this class did not have any prerequisites. I did not expect you guys to learn Python or R programming or anything in order to take this class, but we have an option here for building fairly simple models. And that is going to be the graphical modeler here. Let's take a look at the graphical modeler. And if we look into the processing toolbar, and we look at the graphical modeler here, now we get the model designer. If we take a look, we can see here that we've got a couple of different kinds of inputs that we can introduce into our model here. We've got inputs and we've got algorithms. Our inputs are going to be essentially, if you're familiar with programming, the inputs are going to be the variables, and the algorithms are going to be the operators, or the processes that get run. So in this case, we have some inputs already defined. Okay, I'm going to go ahead and get rid of basins here because those are just going to get in our way. So let's go ahead and remove those layers. And let's go ahead and start up our graphical modeler again. And so let's go ahead and let's define what our inputs are going to be. So the first input that we want, because we know what we're going to want to do, we're going to want to automate the running of our water dot outlet model. And so what we need here first is we need a raster layer. So I'm going to go ahead and introduce raster layer, and this is going to be our flow direction. Okay, so by defining this as part of the model, now this will allow the user to go ahead and define the flow direction every time that they run the model. Similarly, the other thing that we needed was we needed our outlet point. And so to do that, so we're going to go ahead and introduce a point. And we're going to do this for two separate watersheds, right? We've got an upper watershed and then a lower watershed. And we want to calculate it for the upper watershed and the lower watershed separately, and then we'll define what the difference is between the two. So so we're going to go ahead and we're going to put in the, let's go ahead and put in the upper outlet point. Okay, I'm going to go ahead and rearrange these a bit as we go. And then I'll create another point here for lower outlet point here. Okay, and so now I've got my inputs defined, and now I want to go ahead and jump over to my algorithm. And again, what we wanted to do was we wanted to automate a process that the first step of the process is going to be to run the water outlet. So this is under grass, under raster, so the R dot, go on down here to the R dot water, and here's our outlet. So I'm going to go ahead and I'm going to introduce the R dot water outlet, and what we're going to do here is I'm going to go ahead and give this the description, and this is going to be the upper watershed. Okay, and you can see, well, I could go ahead and I could define a layer here and say, for example, we would need the drainage direction here to input that. But problem is that that's then going to be tied into the layers that I have in my current project. And I don't want that. I want this to be a flexible model that can be run regardless of what layers we may have in our model. So what I'm going to go ahead and do, and I'm going to specify this as a model input, and we can see the model input that I want to use here is flow direction. Okay, it's jumping right to that. There's no other choices because the other two inputs are points. Okay, and for this one, I want to go ahead and I want to say model input, and this is going to be a point, and I've already defined this as the upper, so this is going to be the upper watershed, and this is going to take the upper outlet point. Okay, and now you can see it's going ahead and it's created my model here, and you can see how it's already graphically depicting that the inputs are going to be upper outlet point and flow direction here. So what's my next step? The next step is to create a polygon out of this this watershed basin. So I'm going to go ahead and I want to polygonize, and we're going to go from the GDAL version of this is pretty good. So I'm going to go ahead and use the GDAL raster to vector, so you can see that this is nicely set up. And I'm going to go ahead and polygonize. This is going to be my upper watershed and my input layer. So once again, I want to make sure that this is running off of the output from this previous algorithm. And so now I'm going to go ahead and I'm going to say algorithm output. And you can see here where it just jumped right to basin from upper watershed. Everything else is going to be just fine. And I'm going to go ahead and run that. And so now I've got my model. Now I want to do the same thing for, let's make this a little more reader friendly here. So I want to do the same thing for the lower watershed, and you can see what I can go ahead in here and do is I can select my my two algorithms here, and I can just copy and paste using Control C, Control V. And then as I do this, I can go ahead and redefine. So this one is going to be for the lower output. This is my lower watershed. And then I'm going to go ahead and change the output from lower watershed. So now you can see here where I've got flow direction is contributing to both the upper and lower watershed, but the lower outlet point, which I'm going to create by clicking on the map when I run my model, is going to just contribute to lower watershed, and then the output from this is going to contribute to the polygonize of the watershed here. Next thing I'm going to want to do now, the last thing I'm going to want to do is calculate what the difference is between these two watersheds here. And for that, we can just go on back into our algorithms, and we can go ahead and look for difference. Once again, you'll notice that all the algorithms here, these are the same tools that show up in the processing toolbox. Okay, so our vector overlay, and I'm going to go with difference. And as we remember, our input layer, so the way the difference works is it looks for the area in the input layer that is not a part of the overlay area. So our input layer, we're going to go to model output, and this is going to be the lower watershed. What did I do here? Hang on for just a moment. Let me see what I'm doing wrong. Oh, what I did wrong was I did not rename polygonize upper watershed. That was lazy and sloppy of me. So now I am renaming the description here, polygon lower watershed. So now when I go into difference, I should be able to see. Ooh. Yep. No, I want to do from the overlay here, and if I go ahead and I run my model, so I want the lower watershed, and then the overlay layer, I want this to be vectorized from the upper watershed. And then I'm going to go ahead and run the difference between the two there. And I think maybe I'll even go ahead and I will name this as the as my difference watershed. Okay, so we can see here that we've got a very nice flow chart. Some people like theirs vertical. I tend to like mine horizontal. There really isn't a right or wrong way. The only wrong way to do it is illegibly. So, so our process is going to run from our inputs here, which we are going to define as we run the model. It will run through these processes, and then it's going to go ahead and produce this as a final output. So let's go ahead and save our model here. I'm going to go into my model properties, and I'm going to go ahead and I'm going to call this my my difference watershed model. And I'm going to save this, and it's going to ask me where I want to save this. I'm going to go ahead and put this in with my project here. So I'm working here in module 4, and difference. So the model properties here, this name here is going to come up on us again. In fact, let me go ahead and get rid of those underscores because it's just a property. So spaces are going to be fine here. I'm going to go ahead and save this again. So my difference watershed model, the name for this is actually going to pop up. I'm going to go ahead and kill this now. And if I go back to my processing toolbox, you can see that now I should have where is my Where is my model? Ah, I see what I did. The problem was I did save the model, but I did not save the model in the project. So let's go ahead and my model designer here, and I'm going to reopen my difference watershed model and open that up, and everything is fine just the way it was. And you can see this little green button right here, Save Model and Project. This is, and I've now got my nice little model. Give it a second here. And now if I go ahead and close this out, I should now see this. Here we go, project model. So now you can see that I have saved my model to the project, and this is going to go ahead and allow me to run the model within the project. Once again, the nice thing about the way that we've set this up is that this can now be loaded up into any project at all that I've got. So if I've got some other model I've gone ahead and run watershed on, as long as I've got my streamlines and my flow directions defined here, I should be able to go ahead and I should be able to run this model just fine. So let's go ahead and run my difference watershed model. And my flow direction, I need to input this. And here's my drainage direction. And I want to go ahead and define my lower outlet points. I'm going to go ahead and I'm going to zoom in on in here. And here was my lower outlet point. And I'm going to go ahead and define my upper outlet point here. Let's go ahead and say it was this point right there. And let's go ahead and run it. And so now you can see what we've got here is we've got a vector layer. Oh, very nice. We've got a vector layer of our difference watershed. So this is the area that contributed flow to the area between the two outlet points that I've delineated. So, the example that I gave of, measuring the contaminants that are entering into an area is a very real concern, because you would think that finding pollution sources to be fairly easy, but very often it's not, and there can be quite a bit of uncertainty in what's going on between different measurement points. So this is a very real kind of analysis that gets run here. So go ahead and run this. See if you can get something similar yourself, and then we're going to go on to the next section here of part 2. And the next thing that we're going to start doing is we are going to look at land cover layers from the National Land Cover data set. So I'll be with you on that in just a few more minutes.